we all know, concrete is the most abundant composite material available worldwide. Its constituents are mainly cement, water, and aggregates as fillers. Of these materials, cement has the heaviest environmental impact, with a carbon footprint of up to 0.81 kilograms of equivalent CO2, up to 0.90 kilograms of equivalent CO2 per kilogram of cement produced. In a global context, this would mean that the cement production is roughly 8% of global emissions, while commercial flight represents 5%. To better deal with this environmental issue, the use of the implementation of CSMs has been proposed. In the case of this study, this review, calcinated biomasses from 300 to 1000 Celsius are reviewed under the term biochar. Well, biochar are the residual ashes obtained after thermal conversion of biomasses, which are basically pyrogenic residual waste. For the present study, 379 items were considered initially, but after the selection criteria and screening process, it was narrowed down to 20 items. Well, one of the sections that were reviewed is biochar as a functional material, and for this, its physical and morphological properties were assessed or reviewed, as were the chemical properties. Under the physical and morphological properties, we have porosity, particle shape, surface area, and density. Also transfer properties, workability, and filler effect. While on the chemical properties, we reviewed elemental and chemical composition, its relation with degradation and stability of biochar, pozzolanic reaction, and pH. But under the porosity, particle shape, surface area, and density, we identify biochar as a pyrogenic residue of biomass thermochemical conversion. This is a process where oxygen conditions are limited, during which water evaporation occurs first, then is followed by the release of volatiles, and finally the setting of porous carbonaceous ashes. In the broadest sense, biochar is a charcoal-like solid material, typically composed of carbon, of porous carbonaceous nature, and low bulk density. This allows that, from a structural point of view, biochar to have high absorption. This is hydrophilicity, a complex pore network, and to function as an internal curing agent in cementitious composites. Well, in this micrograph, we can appreciate the porous nature of biochar. And this means that while porosity, surface area, and density are important properties for cementitious composites, these are linked. These properties are linked. And for example, density is related with porosity. As porosity increases, density tends to decrease. The same thing happens with surface area. When particle size is decreasing, surface area tends to increase. And in the context of biochar, which is a porous material and tends to have lower densities, depending on the calcination temperature, tends to have lower particle sizes on the lower end, then this develops composites of a lower density. And this is heavily affected by the ratio of biochar replacement. However, this is not all bad news, because biochar composites, cementitious composites, might pose as potential applications as lightweight composites, which are energy efficient. Well, in the context of transport properties and workability of biochar composites, in cementitious composites, several transport properties are important. To name a few, we have water absorption, permeability, thermal conductivity, electrical resistivity, sulfur resistance, and chloride diffusion. As we have exposed before, biochar presents a complicated pore network, regardless of the biomass feedstock, which contributes to diffusion effects and entrapment of contaminants. And its low thermal conductivity and high porosity allow it to be considered as an insulating agent. What is a thermal insulator? Biochar composites are great thermal insulators because of its high porosity, leading to a decrease in thermal conductivity. And this is an important property when developing lightweight composites of concretes. And a thermal insulator is a material that does not conduct heat well. This derives in higher energy savings and thermal efficiency. Another important transport property which affects workability is hydrophilicity, or its water uptake, its water absorption. The more water it absorbs, it tends to absorb water and then eventually release it, increasing the ratio of voids and thus decreasing workability because of this water absorption as well. Well, in terms of durability of cementitious composites, a few important properties are electrical resistivity, sulfur resistance, and chloride diffusion. Since free chloride ions are a major threat to reinforced concrete due to the depassivation effect, leading to corrosion and the formation of solids on the surface of the reinforcement. These volume increases derive in internal stresses and the eventual cracking of the concrete layer, thereby reducing its service time. The findings of the present review suggest that biochar addition helps to preserve strength in an 8 to 11% proportion even after 120 days of exposure. In the case of sulfates expansion, they experience a reduction in the order of 60 up to 68% in contrast with reference. Both cases correspond to a 1 to 2% substitution of wood and rice husk biochar in a weight-to-weight basis. Well, not all biochars tend to react with cement in a pozzolanic way or in a latent hydraulic way, and might pose or might be a strong candidate for the filler effect, which is the filling of voids, and these particles act as nucleation sites. Filler effect is characterized by being inert and non-reactive on its own. However, it favors the development of a more densified microstructure. This happens through two mechanisms. The first, the filling of interstitial spaces between cement grains, as we can see in the pictures, promoting densification. And secondly, an increase in the surface area available for the nucleation of hydration products such as CSH gels or Portlandite, CH, among other hydration products. This is where elemental and chemical composition are important, because we are looking for high contents of silicon dioxide and calcium oxides. This is mainly because these two oxides help to determine if a material has potential as a pozzolanic material or a latent hydraulic material. Otherwise, it might as well act as an inert filler. Another important aspect of biochar, which is worth mentioning, is its HC ratio and its OC ratio. Its hydrogen to carbon ratio and its oxygen to carbon ratio. We expect low values for these two ratios since this describe the stability and longevity of biochar inside the cementitious matrix. According to research literature, an OC ratio of 0.45 has an estimated service time of 100 years in an inert nature and without degrading itself. In the present table, we have all the studies that were considered for the present review. And as we can see, there are some biochars which have lower than regular OC ratios. Also, according to literature, OC ratios under 0.40 would mean an stability and service time of up to 1,000 years. So, as we can see, there are some, like it's the case with poultry litter and rice husk, some ashes that have higher OC ratios while presenting lower HC ratios. This is highly dependent on thermochemical conversion temperature, because the higher this temperature, the more carbon content, and thus a lower OC and HC ratio. In these studies as well, the highest HC ratios correspond to the lowest temperatures, indicating a less aromatic biochar. In other words, less stable carbon in biochar. So, one of the solutions to obtain a stable biochar for use in cementitious composites would be to increase the thermochemical conversion temperature. And this has been evidenced by an absorption mechanism shift from cation exchange, CEC, to physisorption, affecting its absorption capabilities as well. Another important aspect also related with HC ratio and OC ratio is its yield. The higher the temperature, the less yield obtained. So, on the same vein, while these ratios decrease, also the yield or the biochar obtained decreases. Well then, pozzolanic reaction and its relation to mechanical properties are of utmost importance for biochar composite materials. As has been explained before, the reaction between silicon dioxide and calcium hydroxide with water produce hydrated calcium silicates. In this context, when any RCM, any supplementary cementitious material, has amorphous silicon dioxide, these oxides can react with the free and available calcium hydroxides available in the hydrated cement matrix. Thus, leading to the further production of more hydrated calcium silicates. Why is this important? Because increasing these calcium silicates derives in further increase in density, another hydrated products like CASH or AFM phases, and thus developing higher strengths in cementitious composites. There are many biochars which have high contents of amorphous silica dioxide, which are rice husk ashes, sugarcane bagasse ashes, and even poultry litter ashes. And in the present review, it has been demonstrated that replacement ratios go from 1% up to 20% in a weight-to-weight basis, and still obtain pretty much satisfactory results in terms of strength development. Well, the main findings of the present review were that biochar dosage and parent biomass feedstock played a critical role in the overall properties and strength development of the resultant composite. Dense temperature, feedstock, the involving conditions, and the dosage are really important aspects when one is trying to develop eco-efficient cementitious composites which still compete with conventional blends. The second thing would be dosages of over 10 to 20% in a weight basis, demonstrating to increase compressive and flexural strengths. Incorporation of biochar reduced the composite density. However, it acts as an internal curing agent. As has been mentioned in this review, this hydrophilicity property of biochar allows for this material to gradually release water to the cementitious matrix, and thus hydrating the cement grains and producing even more hydration products. Dosages of 2 to 8% of cement replacement enhance properties such as water absorption, capillary porosity, and even decreased water penetration due to saturation, which is an effect linked with the filler effect. And the last one would be biochar incorporation to cementitious blends also resulted in an abatement of GHG emissions for 59 to 65 kilograms of equivalent CO2 for each ton of produced composite. For further research opportunities and research voids yet to be filled, to the best of our knowledge, there are now studies which statistically correlate the thermochemical conversion parameters such as temperature, heating rate, residence time with certain properties of biochar related to durability in cementitious composites such as elemental and chemical composition, OC and HC ratios, pH, density, porosity, surface area, and mechanical properties. To establish the statistical significance of any of these properties in relation to long-term expectation of biochar cementitious composites in terms of durability and even acting as carbon sinks. The second great opportunity that was identified is that, notwithstanding the lack of research about this particular subject, it can be inferred that biochar amended composites pose as promising materials for the development of novel cement-based materials, such as pervious concrete, water purification, heavy metal removal, soil stabilization, bacteria carriers, heat, and sound isolators, among many others, while simultaneously acting as carbon footprint reduction agents in cementitious composites. Assuredly, further investigations are needed to provide more precision and certainty over biochar containing composites performance. Well, with the selected references from the extended review